Okay, so I'm working for Dante, which is a company non-for-profit, and we are operating research networks in Europe. Okay. So this presentation is about Multicast, and it's in two parts. The first part is about the Multicast that we have operated in our previous network, 10.5. And this part is written by Jan Novak from Cisco. Jan Novak was working for Dante from 1999 to year 2000, and he was responsible for this project of Multicast on our previous network. The second part is about the new network that we are currently deploying, and its name is GEANT. So I'm working on this second network, and I'm involved in Multicast. So we were thinking that it was worthwhile to make a presentation about the both network. That way you can see the historic of evolution of deployment of Multicast and for the research networks in Europe. So one word about Dante 10.5 GEANT. Dante already said that this company is operating European national research networks, pan-European research networks. So 10.5 was our previous network, and it was an ATM-based network built on OC3 links, and it has been integrated in year 2000 at OC12 capacity. The network where I'm working now is GEANT, which is the successor of 10.5. So this new network has been launched in December 2001, which is quite recent. And this network is a 10 gigabit pan-European network. So the first part of this presentation is about what we have done on 10.5 and the operational multicast experience we gained from this network. One point about history. So everything started in 1998 with the endpoint topology that you are on the slide. Possibly you don't see very well, but just the black square are workstations across Europe. And those workstations are interconnected with DVM-RP tuners. And that was the first multicast network based on 10.5 topology. So you can see the command. It was a typical mess of DVM-RP tuners and with a lot of routing problems. In 1999, appeared in 10.5 the first pin-sparse mod domain. This setup has been built for the retransmission of the Oslo IETF, and in the core backbone, two routers were enabled multicast, the router in Netherlands and the router in Sweden, and one router was gateway, the router in Germany named DE, was gateway between this pin-sparse mod domain and the remaining DVM-RP cloud. We were pairing, so for this first pin-sparse mod setup, we were pairing with SoftNet and NordUnet in a pin-sparse mod NBGP and MSDP fashion. Based on this this operation was successful and the retransmission very good. Then it has been decided that 10.5 was going to be enabled multicast in all these routers, which means that we were going to extend pin-sparse mode to all the core routers in the backbone. It has been confirmed that the multicast code on the router was stable, the CPU usage okay, MBGP didn't break, unicast routing, and they decided at that time that they will enable pin-sparse mode and they won't support any more DVM-RP because in a management point of view for NOC it was impossible to manage two different types of multicast domain. So what we've done is from 1999 to year 2000, we have canceled the GVMRP cloud, and we have connected all our customers in a pin-start mode session only, and BGP and MSDP. So in year 2000, that's what looked like 10.155. You can see the cycle with the acronym inside. That's the name of the countries and the routers, the point of presence of our router. So SE stands for Sweden, and L for Netherlands, D for Germany, etc. So we got those core routers which were fully meshed with NBGP and MSDP. So that's the internal multicast backbone. And we were peering with our customers. So that's, we were peering with you can see the red lines or the black lines. So the red lines represent the connection we got with them, which are what we call native multicast, where on the physical access you have unicast and multicast traffic. And the black lines between our core routers and our external peerings represent dedicated access for multicast. So in this setup in year 2000, you can see that in Europe we were in a non-congruent topology where some countries like Belgium or like Czech Republic or some others had dedicated access for their multicast. So one word about the performance and the operational experience in 10.155. This network was based on 7K routers, so we monitored CPU parameters and memory, etc. We got about 1,600 forwarding routes in the enrouting table. We got up to 8 outgoing interfaces on the router, which means that's the multicast tree. And we got up to 20 megabits of multicast forwarding data on one router. The usage of PIM sparse mode resulted in an increase of CPU up to 5 to 10%. For the memory, we got at that time 3,000 SA messages in the MSDP cache, and we got, well, still this 1,600 forwarding in trace for the mRoute, and we got up to 10,000 routes in the MBGP routing table. These parameters didn't represent a significant memory usage. So, because we deployed this model of PIN sparse mode and BGP, and because this is an inter-domain inter-domain multicast, then you have to use MSDP for the discovering of the sources from the other domain. So when they started to use MSDP, then because people did not know too much this protocol, in an inter-domain context, we had to face misconfigurations. And this slide represents the common misconfiguration that people have done in inter-domain context. So the use of default peer or the configuration of mesh group between autonomous systems cancel the MSDP RPF check and could create MSDP loops, MSDP SA loops. And the graph that you can see at the bottom of this slide is the CPU usage. And you can see a massive increase of CPU usage on the right of this graph, which represents an MSDP storm. Well, MSDP as well, they got some problem with implementation. This list is possibly not exhaustive, but they had to fight with some bugs, and well, all those ones are already fixed, but they had to fight with SA messages which were recreated by the incoming source group joins or the IP-MSDP redistribute commands, which was re-originating non-essays. But I would say that this was the problem at that time, but today you can have some other problems with some other iOS. So at that time, so for Tenon Sci-Fi, we put in place an MSDP monitoring for MSDP and for MBGP. So for MSDP, we used a software implementation from Steve Rubin that we have adapted, and we were monitoring the number of RP originators, the number of groups per source group, and essay messages per minute. So just to give you an example, here in this graph represents the number of RP originators seen in Tenon Sci-Fi. And you can see that week 51, we got, okay, I'll come back. Week 51, we got an outage in the core backbone, and we lost connectivity with the US. And you can see that the number of RP represented in week 51 and week 52 are the number of RP originators in Europe, because we were completely disconnected from US. Well, when I spoke about this graph with some people, they told me that you were disconnected for 2 weeks to the US. And what you have to know is that our topology was non-congruent, which means that we got an ATM PVC dedicated for multicast for the connection to the US. So this ATM PVC was broken for 2 weeks, and then it's why you see this outage for 2 weeks for multicast. But unicast was still working at that time. For MBGP monitoring, we put in place as well an MBGP peering between a workstation and a router, and we used a software from Merit. We were collecting updates with the NLI multicast only, and we were monitoring the stability, the number of routes, and the number of autonomous systems. So this graph represents the number of routes originated by one AS. This is the blue line. And in the green, you can see the number of updates originated by the same AS. So each time you have a green column, it represents instability. You can find details about this usage of the monitoring that we put in place for MSDP and MBGP in the different publications and the different URLs in this slide. The graph value that you will get are historical value. So the conclusion for Tenon Sci-Fi and the operation of multicast. First of all, the fact that Tenon Sci-Fi itself changes topology and went for pin-sparse mode, MBGP, MSDP architecture. This change initiated the same change in the National Research Network, our partner. So they were at one point dealing with DVMRP and pin-sparse mode, and then they get rid of DVMRP to be purely in the same architecture as us. The second point is that we were at that time, the unicast and multicast were non-congruent in Europe. We understood that an MSDP peer doesn't need to be RP. Because MSDP was a new protocol, this was not really clear at that time. It was very difficult to make people understanding the usage of multiple routing tables, and one for unicast and one for multicast, and the RPF check associated with. So it was not really understood, and I would say it's still difficult to make. I find it very difficult. A lot of people don't really understand this concept of having different routing table and one dedicated for RPF check or things like that. The next point is the inter-domain multicast debugging. Well, at that time it was clear that it was very difficult to fix one problem in one week due to the multi-domain where multi-people have to be contacted for one given bug. I would say it's still the same now. It's very difficult. So this is the part number 2, and I'm going to present GEANT and its deployment. So in blue you have 10 on size 5. That was the coverage of 10 on size 5 in Europe, and all the countries in blue were covered by 10 on size 5. In brown, that's the country that we have added with GEANT. If you want to have the name of those countries, or if you want to have the resolution of the acronym that I'm using in the presentation, then you can go to this link, GEANT Multicast/map, where you have a table with the name of the countries and the acronym that I'm using in the presentation. So, GEANT. GEANT is a 10 gigabit backbone, and you will see in the few slides precisely where we have 10 giga links in Europe. The services that we are deploying currently are the standard IP service, where we are offering IP traffic from customer to customer. We call them National Research Network. We are offering the multicast service, and that's what I'm talking about. And we are working as well for the replacement of some other services that we were providing with 10.5.5. One is named Managed Bandwidth Service, and we used to provide VPN layer 2 with quality of service by the way of using ATM, PVC, and VPs across Europe. We got rid of ATM, so now we have to find a way to provide the same type of service. And there are 2 services pending, one which is currently piloted, which is the premium IP service based on this serve, and the second one is the layer 2 VPNs, which will be based on MPLS VPN layer 2. We are working on some other topics like security and IPv6 as well. So GEANT customers are peering. I wanted to show you in this slide that so for Unicast we are peering with 27 countries in Europe, but for Multicast we are going to peer with 24 countries in Europe. And just to show you that basically Unicast and Multicast have the same coverage in Europe, and it's not, Multicast is as important as Unicast. For the research and commercial peering, so for the research peering, we are peering with Abilin, Canary, ESNet, and ESNet. We are peering in Unicast, and we are currently deploying the peerings as well with them for Multicast. For Multicast, currently we are peering in Europe with Infonet, and in the US with UUNet. The next standard is achieved, and our next interconnectivity for commodity traffic is going to be with Global Crossing and KPN Quest, and we expect with them to peer in Unicast and Multicast as well. So GEANT Multicast customers, I thought this table for 2 reasons. First of all, you have the list of countries where we are peering in Unicast and Multicast. You have the access, which is the type of link that those countries are connected to us. So you can see that we have STM16 with them, we have STM4, but we have as well some slow links like E3 for the small countries. The next column is the multicast type, and you can see that all the people who told us that they were interested in multicast are going to be native connection, which means that they are going to use their main access for unicast and multicast traffic. So one word about the design that we have chosen for GEANT. So based on the experience we got from 10 on Size 5 and guidelines that we got from multicast experts and the laboratory tests we've done with Juniper, so we have defined a design, and I'm going to present you this design. You can find all the details at the URL written in this slide. So we went to the lab we made a lab with Juniper in November. This lab had the aim to represent, to simulate our core backbone, and this is the rectangle that you can see. And we configured this core backbone precisely like it is done in GEANT. And then we have simulated some National Research Network peering, and that's the colored cycle that you can see in yellow, green, and red. Here the objective for Multicast is that basically we support transit multicast, which means that we have, if the yellow cycle wants to send or receive multicast to the green cycle, we must support it, and in any way. And we want as well to send and receive multicast inside the core. So the core itself can generate multicast or receive multicast. So first of all, we built MBGP, and in GEANT we have basically 20 routers, so, well, 1920 routers. We have a full mesh of MBGP between all those routers, so we've done that in the lab. And we have external MBGP peering between our access routers and our National Research Network partner. Then we were looking for a design where we would have a subset of routers in the core activated for MSDP, and doing kind of multi-op MSDP. I'm going to try to use the mouse. I don't know if I can. No, I can't do it. Okay. And we couldn't. So we wanted to do this setup with MSDP, but the internal rules of RPS check of MSDP can't authorize you to do something like that, because if you take the router, I don't know if you can read the name, but the router Gallium here, it will accept the MSDP SA messages from the yellow autonomous system. It will accept it from its MBGP peer, which is manganese, and not from iridium. That's the internal MSDP RPS check. So we had to go for a full mesh of MSDP internally, which is following the full mesh of MBGP. Based on that, we then started to make multicast traffic between yellow and green cycle and etc. And we found a bug in Junos 5.0. This bug has been fixed very quickly, and now everything is fine, but this proved that the lab was very useful. And we decided to reduce the number of SA messages in the core. We decided to use mesh group, MSDP mesh group. Well, so for pin-sparse mode V2, we have all our interfaces which are enabled pin-sparse mode. We have in our core backbone 3 rendezvous points, which are using a private unicast address. So basically, one pin-sparse mode domain means one rendezvous point. That's the minimum. We have 3 rendezvous points because for backup reasons, and we are using a unicast address, which means that for our internal sources, the router where those internal sources are directly attached are going to register to this private address. And if we have one rendezvous point which is broken in the backbone, then we still have 2 other rendezvous points which are still available and reachable with this private IP address. For the other domain, which is not our autonomous system, but our national research partners, they have their own pin-sparse mode domain, and they have their dedicated rendezvous point in their domain. We are not providing them any rendezvous point. They have their own rendezvous point. This is the physical topology of GEANT. So the square represents the point of presence in Europe, and in each square you have an acronym which represents the name of the country. So if I pick up one square, for example, UK stands for United Kingdom, SE for Sweden. So you can see that, for example, between UK and Sweden, we have a red line, which is a 10 gigabit line. And if you pursue like this, if you take time to look at this physical topology, you can see that we have 10 gigabit trunk between UK and France, France and Germany, Germany and Sweden, Germany and Czech Republic, Germany and Italy, Italy and Switzerland, Switzerland and Austria. So that's the 10 giga core. You have black lines which represent 2.5 giga links, and we have a subset of them. We have a lot of trunks at 2.5 gigabit towards the east in Europe. So Czech Republic, Slovakia, Hungary, Austria, and Germany are connected at 2.5 gigabit. And then you have another subset of lines in green, which represents STM4, so 622 megabits, and pink lines, which are 155 megabits. The numbers, the small numbers that you possibly can't read are the metrics of OSPF. And what is doing OSPF there in this slide is because the blue points represent the rendezvous points that we have put in our core backbone. We have 3 rendezvous points, one in UK, one in France, and one in Germany. And they are distributed that way because we tried, so those rendezvous points are dedicated for our sources that we are originated. And we managed that those sources, we managed to distribute the sources equally among the rendezvous points. So basically we have something like 6 to 8 sources per rendezvous point. And I will give you more details where those sources are coming from in this presentation later on. The name written among the square are the National Research Network that we are pairing with. Okay, so with this design we have MBGP and MSDP. MBGP is the routes from MBGP are put in a different routing table, which is for Juniper routers INET2. And well, in fact, our topology is a congruent topology in Europe between BGP and MBGP, which means in a clear words that unicast and multicast is taking the same physical access for all our partners in Europe. So we could go and use INET0 for the RPF check. But the thing is that it's more flexible to have 2 different routing tables and have your unicast routes into INET.0 and your multicast routes for the RPF check into INET2. For the MSDP, so we have a full mesh between 19 routers in our backbone. Those routers are access routers and core routers. We don't have a notion of access routers and core routers. They have both functionality. We are using MSDP mesh group. And the internal MSDP peering is done with the loopback addresses. Of course, we are not using any cast address for the internal MSDP peering. We are using loopback addresses of the router. For the external MSDP peering, we are peering between our router, GEANT access router, and the NAN router. So this is a logical view. And if I pick up UK router, for example, which is the blue spot written with UK, then you can see the current peering that we have this router, the MSDP peering. So we have an MSDP peering with GEANT and an MSDP peering with an autonomous system named GTIN, etc. So that gives you the logical view of MSDP. For MSDP filtering, we are following the filtered assay which is recommended at the IETF, and we authorize the local scope 239.194 through GEANT. this is another logical view of multicast and unicast coverage for GEANT is research peering and different type of peering. So in green you have GEANT and its partners, the National Research Network. I written here the name of the network, GFN, is from Germany, Journal from UK, etc. So this is enables unicast and multicast. In blue you have the research peerings that we are currently deploying. And we have a direct peering between GEANT and Abilin. We have a direct peering between GEANT and GTIN. And we have remote via GTIN. We will peer with, we are peering in unicast in case with ESNet and CANET, Canary. GTIN is a global terabit research education network, so that's a new network which is initiated by Dante and Abilin people. You can find details at the URL which is written between this under this acronym. And in yellow, that's the access to internet, and we expect to enable this is under deployment as well, so the unicast deployment is not yet achieved for the yellow cycle, and we expect to connect with KP and Quest and Global Crossing in unicast and multicast. So access to the service for our National Research Network, it's going to be via the primary access, and nobody asked for GIE tunnel. For the operational procedures, we are working on it, but we expect to deliver the same level of service for multicast as what we are doing for unicast. We have more, for the multicast we have more, with our NOC we have more dedicated people and allocated people for monitoring multicast. And for the troubleshooting, we expect to extend the trouble ticket system to the multicast incident as well. So one word about monitoring. We are using a tool which is named Beacon, and this tool is originally has been developed by ANR people. This tool relies on a number of agents which are spread over the network, and those agents are sending and receiving simultaneously multicast packets which are timestamped. And those agents are reporting to a central server about the packets that they have sent and received. And you get, okay, so we have some national research, well, we have some groups that the TFNGN group is a kind of international research group where people are testing technology, and they did test this Beacon tool, and they did recommend us to use it for the deployment of GEANT and for its monitoring. Some people from the TFNGN group have worked on the code as well, and they have added some functionality, and you have the set of URLs here if you are interested by their work. For GEANT, we are deploying currently two matrices. One internal matrices where we have installed an agent in each point of presence in the core backbone, and one external matrices where we invite our partners, the National Research Network, to install one agent in their network and to join the matrices. So you obtain something like that. So maybe you don't see very well, but if I pick up S5R5, this represents one agent in one workstation, in one point of presence in our network. And this S5 is from Spain, for example. And we have something like 13 or even more agents in our core backbone. And all those agents are sending and receiving multicast traffic to each other. So here with this internal matrix, we are currently monitoring the connectivity. which means that if we have loss of connectivity in the core for multicast point of view, then we can see with this matrix the outage. The black cross that you see between S5 and R5, that was an outage due to the misconfiguration on the Spanish router when pin source mode accidentally has been removed. So you can see that the agent in Spain can't communicate to any of the other agents via multicast. We are expecting to install some other monitoring tools, and we have one which was created for tenant side, and that we are deploying again in the network, which is a pair group monitoring tool. That's a homemade tool, and it shows traffic per multicast group per interface. This tool relies on the IP en-route NIB, and currently with 5.0 we can't exploit this IP en-route NIB, so we expect to be able to use it with 5.1 when we will be with this iOS. And we expect as well to redeploy MSDP and MBGP monitoring tool. So the conclusion is, about the deployment status for multicast. So currently we have enabled 4 or 5 customers with multicast in Europe, and we are still deploying them. The rate is something like 1 or 2 per week. You have to know that each time we enable a new customer, so we are debugging inside, we are controlling the SA, the MBGP route, so it's why we are taking time, and we can't deploy 1 per day, but it's something like 2 per day. Our topology is congruent in Europe for multicast, so that was the difference with what we've got with tenant side. You can follow online actually the current deployment. If you go to this URL beaconserver.geant.net and you type this support, then you can see the National Research Network agent. And if you type the same but you remove the 1, then you can see our internal beacon matrix. And you have all the details at the URL net/geant multicast if you're interested in this area. We want to thank all the people that we are working with for multicast in Europe and the US, because they are doing a good job with us. And question? No question. Thank you.